Welcome to today's webinar. My name is Matt Bichelle. I head up product marketing for Aerospike. It's my pleasure today to have Srinivasan present today the 4 essentials to a modern distributed database. Today's topic, as Srini will be presenting, is a key technology discussion to the underpinnings of Aerospike and some of the foundational principles of how it was created. And so without further ado, Srini, do you want to begin?
Hello, everybody. I am Srinivasan, CTO and founder of Aerospike. In this presentation, I'll take you through some of the essentials of a modern distributed database. We're going to talk about 3 major topics: scale out, scale up, followed by how we implement distributed transaction management with strong consistency. But first, let me take you through, Let me take you through the mission critical use cases that are the basis of the work that we're describing here. As you can see this across a wide variety of industries and use cases, there is a requirement for very high throughput, low latency transactions, which can be highly available. For example, something like fraud detection would require to generate a fraud score for transactions in progress by looking at a couple of thousands of items to generate a really good fraud score. And this has to be recent data, behavioral data. And this should all happen within a couple of 100 milliseconds. And there are many other use cases I won't go into, but every one of them requires a real-time SLA with the ability to handle recent real-time data in order to make accurate and better decisions. So going forward, as I pointed out, we will first spend some time on the basics of scaling out in a distributed database. In Aerospike, we have tackled this problem by building out a shared nothing database cluster. Such a cluster essentially consists of a number of nodes, which is shown in the bottom part of this picture. Each of this node is identical to every other node. And that's really important. And every node is not only identical in terms of its capabilities, in terms of the amount of storage and CPU and networking capacity, memory available in the particular node, it is also identical in terms of the code that runs in it. So there is no single master. Essentially, it's a distributed system with every node being identical and be able to perform various tasks that are required to run such a distributed database. Additionally, the system, because it has no single point of failure, is able to also run with no hotspots. And there's a lot of engineering involved in ensuring that. One of the special things about Aerospike is the fact that the clients themselves are intelligent and are able to share some of the mapping data of data to nodes so that they are able to reach the target node for a particular transaction in one hop. And the load balancing is done on the client in software. And essentially, it is able to adapt to changing cluster conditions. And that gets into dynamic cluster management. The cluster is dynamic in the sense that nodes can arrive and depart at any point in time without interrupting the flow of transactions. And the ability of data to move around based on node addition in order to rebalance the system properly is all done automatically. And rolling upgrades, of course, can happen with no outage of the service, et cetera, et cetera. Finally, in the presence of node arrivals and departures, there is need sometimes to move large portions of data in order to rebalance the data within the cluster. And these are typically long-running transactions, and these have to run with the right level of priority without impacting the SLAs committed to these other transactions, which are typically very short, submillisecond reads and writes with very high throughput and requiring low latency. So the interplay of the long-running tasks and transactions is something which is also done in this system by proper prioritization of these different tasks appropriately. Aerospike actually uses a divide and conquer algorithm. In the data partitioning scheme used by Aerospike, every key is hashed using the RIPEMD 160 function, which is a cryptographic hash. It is extremely random. And out of this digest, which is created by the RIPEMD 160, which is a 160-bit or 20-byte digest, 12 of those bits, and these are randomized bits, as I explained, are used to determine the partition ID for that key. 12 bits give a 4096 or 4K set of partitions, and each of these partitions can then be mapped to nodes in the cluster. On the right side of this picture, you see a table on the top which maps the 4096 partitions to nodes in a 5-node cluster. If the cluster has 2 copies, the first 2 columns are relevant. If it is 3 copies, the next, first 3 columns are relevant in this particular partition map, and so on and so forth. When, in this particular case, node 5 goes out of the cluster, and it has been there before, and it just either it is removed due to essentially the node going down for a rolling upgrade, or maybe there was a network glitch which made it essentially isolated from the rest of the nodes in the cluster. That partition map is suitably adjusted to remove node 5, and then you see that in the second row on the right side of the picture, and then the node 5 is added back into the partition map when the node comes back. Now, this kind of mechanism is essentially computable given the list of partitions, which is always 4096, and the IDs of the nodes. The way this partition map can be assigned is either to minimize the data migrations that are happening in the system when nodes arrive and depart. And that's essentially the original algorithm that Aerospike used. What we discovered was in large cluster sizes, running up to 200 nodes, when you end up having just 20 partitions per node in average, there could be skew of up to 4 or 5 partitions between 2 nodes. So one node could have 18 partitions, the other one could have 22 or 23. And what this created was an imbalance in terms of the transactions that are being directed, which are proportional to the amount of data in the node, because this whole thing is fully randomized anyway. And this meant that the node which had more partitions ended up hitting limits earlier. And even if one of those nodes hits a limit, all the nodes essentially are now performing at the lower level of transactions that the first node hit. Now, in order to adjust this, at Aerospike, we implemented certain uniform partition balance adjustments. This algorithm essentially assigns the partitions randomly up to a point. And after a while, as it starts assigning partitions to nodes, it starts to balance them out. What the trade-off therefore becomes, essentially, you are making it more expensive to do data migration. So the trade-off of minimizing data migrations is relaxed in order to essentially generate uniform data partitions. And as you can see in this picture, there is more readjustment required when we use rack awareness, which we will describe in a few minutes. The most important thing to notice here is there are trade-offs, and Aerospike provides choices to deployments to take advantage of whatever it is that the particular requirement for a deployment happens to be. More details on all of this and the algorithms described in this particular talk are present in both internal documents, but also in published papers at VLDB, the latest one being the one published in Vancouver in August of 2023. And you can definitely get access to those. The system, based on the partitioning algorithms I described earlier, is self-managed. Essentially, there are multiple components. One is the heartbeat subsystem, which discovers when nodes are arriving and departing from the cluster. The clustering subsystem, which, without having a single dedicated master, able to elect a master temporarily in order to form a cluster and then maintain the list of nodes in the cluster. The partition map that I talked about is based on the presence of these nodes in the cluster. And given nodes are added and removed from the cluster and the partition map being changed based on the arrival and departure of a node, what happens is there's an exchange subsystem which manages the asynchronous copying of data or migration of data of partitions, if you will, from one node to the other. And you can see an example on the picture to the left, where we are adding an additional node to a 3-node cluster. A 3-node cluster with 2 copies, or replication factor 2, in steady state will have 1/3 of master partitions available in each of those nodes, and 1/3 of the replica partitions available in each of those nodes. When you add a new node, 1/12 of master partitions from each node has to be delivered to the new node, and 1/12 of the replica partitions has to be delivered to the new node. So eventually, when all of these movements or migrations are completed, the data rebalancing is complete, you will end up with a 4-node cluster with 1/4 of the master partitions in each of the node and 1/4 of the replica partitions in each of the nodes, which means half the data is available in each node. It's a 2-copy system with 4 nodes. That's actually, makes sense. Now, having described scaling out, we also focused a lot in Aerospike on scaling up. What that means is the ability of the system to take advantage of every aspect of processing, storage, and networking capacity that is available within a node. In order to do that, we leveraged SSDs very heavily. One of the most important things about Aerospike algorithms is our ability to treat the data available on SSD to be real time. What we mean by real time is we are able to deliver sub-millisecond access times on data available in SSDs for both reads and writes. In order to make this happen, we have implemented certain specialized algorithms which enable, which leverage the random access reads from data from SSDs. So we split the data and the index in such a way that we keep the index fully resident in memory. And because the index is fully resident, it points to the actual data item on the SSD. So it's able to read it within a millisecond. Now, writes cannot be done in place on SSDs because of wear leveling issues, where you could burn out portions of the SSD if you overwrite on those cells too much. So what we do is we implemented a log structured file system with large block writes and copy and write semantics, so that SSD writes are gathered in memory in large buffers and then flushed to disk. What this also allows us to do is to deliver and very heavy read loads in the presence of very heavy ingestion or write loads because of the way we do the writing. Everything is highly parallelized in the access to SSDs because you can stick dozens of SSDs on nodes in some of the large nodes. And what this also implies is with multi-threading and the ability in the background of running a continuous non-disruptive defrag, so we don't run out of space on disks at very high throughput of writes, for example. Other databases are not able to deliver the uniform, predictable performance of sub-millisecond access to reads and writes across the entire database because they typically use a buffer pool-based system where you have to bring the data from storage into a page cache in order to read it. And this essentially means that there is always some of the initial reads which could miss the page cache. And that's never going to happen in Aerospike because the index is fully resident and the data access is directly to SSDs. And the end result of all of this is we have increased the amount of real-time data that you can store in a node And this is now proportional to the amount of storage, that is the amount of SSD storage available on the node, and not just the DRAM available on it, which means the number of nodes in a large Aerospike cluster is typically an order of magnitude lower than those of comparable systems, which have to store all of the real-time data in DRAM. Just storing all of the data in SSDs increases the amount of data that is available for real-time access per node by 10x or even more. In order to make this actually work in practice, we also have to be able to run 10 times the number of transactions per second on each node. SSDs can be set up in parallel, as I explained already, and this means that these particular transactions need to also go in parallel through memory. An Aerospike uses multi-threading. It's written in C. It's highly efficient. We use techniques like CPU pinning, NUMA pinning, and also binding threads to specific network queues, using parallel network queues and making sure a single CPU doesn't bottleneck on network dispatching network requests. And there's a whole bunch of techniques that we use to be able to drive very high throughput in terms of transactions per second through a single node. You can see on the right some basic numbers on a simple NUMA CPU pinned system. This was done in collaboration with Intel a while ago, but it's about 8.6 million transactions per second can be pushed through the system. However, Intel also had invented some technology on the NIC card, which is called application device queues. And what this means is it enables the application queues on the network to be directly linked to the CPU's threads, which means what we can deliver a lot more transactions per second when you use those kinds of isolated and network cards, which are aligned basically with threads and CPUs. Now, in practice, it is very unlikely that we would need to run this many transactions per second on a single node, but the fact is the headroom exists in order to compress all of the real-time data into smaller set of nodes. And that's essentially how Aerospike is able to run very high throughput, low latency workloads at very high scale on small cluster sizes, as small as 10 or even a few, fewer than that, all the way up to 200 and more. All of the performance that I talked about in terms of both the scale out and the scale up, Aerospike has used to develop transaction algorithms which provide strong consistency. And the high performance enables us to take certain possible routes in building these algorithms that are probably not available to other systems which might be much slower than us in terms of leveraging the various underlying infrastructure. Here is an example of how you implement a roster-based strong consistency scheme. Aerospike does not use quorum. Our quorum essentially is write all and read one copy, because we can get away with it due to the performance of writes and reads in this particular case, and due to the networking optimizations I talked about, as well as the CPU and storage optimizations. Now, in this particular case, these algorithms that we've designed enable us to make the system be available in certain common situations. Now, let me take you through a couple of interesting rules here. In this particular case, I have mapped a single partition onto a roster. A roster is a set of nodes that form the cluster. In this case, it's a 5-node cluster, nodes 1 to 5. And the particular partition P has the master copy on node 5 and the replica on node 4. When the system splits, in this case, the cluster splits into a cluster of nodes 1, 2, and 3, and another cluster of nodes 4 and 5, this partition P, based on the rules that we have, contains both the master and the replica. This is a two-copy system, and there is no other data for this partition in any of the other 3 nodes. So this particular partition stays alive for both reads and writes with strong consistency in the smaller cluster, which is subcluster, which is the nodes 4 and 5. Now, if the split happens in a different way, let us say the master copy, the node 5, splits away. Either it's down for a rolling upgrade, or maybe it got disconnected through a network glitch, and so it's just running by itself. In either case, it's isolated. and the other 4 nodes, 1, 2, 3, and 4, essentially are together as a cluster. Remember that the entire roster is known to every node. So they know that one node is missing. So all of that can be computed. Now, in this particular case, the rule goes that because this is a majority cluster, it's got 4 nodes, and this one has only 1, which is out. In the minority cluster 5, even though it has the master copy of the partition, the data becomes unavailable. And what happens in the other copy, in the other cluster, in this case, the cluster with nodes 1, 2, 3, and 4, what you have there is the replica, which gets promoted to master, and an additional replica of the partition is created because every write has to have 2 writes in order to make sure that it is consistent and durable. And essentially, that's essentially what happens. Now, if the node 5 rejoins this cluster, let's say we are doing a rolling upgrade, node 5 went down, it's got upgraded, it's come back and joins it, and then node 4 is going to be taken down next. Between the node 5, which has all the old changes, the old copy before the cluster was split, and node 3, which has all the new data, between those 2 nodes, you have all of the latest data required to answer any request from a read or a write. However, a read might end up being slower in the situation when node 4 is not available, but node 5 and node 3 are available, is essentially because you might have to check with both node 5 and node 3 to get the latest value for a particular read, because node 3 could have the latest copy and node 5 might have the older copy because it was out for a little while. Now, all of this is actually fairly complex, and we have documents and papers we can share with you, both published publicly as well as internal Aerospike white papers. I encourage you to read some of these items and also, essentially get, in order to get more knowledge about it. Also, there are cases, and which is what is shown in the last row here, where the split brain, or the number of clusters, the way in which the clusters split due to network glitches, might end up with no availability for the partition P in this case. In this case, there is a cluster with 1, 2, and 3 got split from from another cluster, which is just node 4, and another subcluster which is node 5. In this case, partition P is not going to be available for read or write anywhere here. So this is essentially the result of the CAP theorem. There are cases where availability will be kind of sacrificed in a strongly consistent system, because that's kind of how the CAP theorem works, because partitions are inevitable, network partitions. So fundamentally, what Aerospike does with all these rules is we can maintain 100% availability of a partition somewhere in the split brain, the two-way split brain. It may not be in both of the split brain clusters, but it'll be at least in one of the two. And 100% availability of the system on a rolling upgrade, where, even with the replication factor 2. Here is a simple example of how we do writes. Writes, as I mentioned, was a write-all kind of mechanism. So in this particular case, it's a 3-copy system. The write goes from the client to the master. The master coordinates the transaction across the other 2 copies. And essentially, it'll do this in parallel, of course. And then once all of the copies have responded to the master, master will commit the transaction, the write transaction, and then it will communicate the commit state to all the replicas. Now, the important thing here is we can support linearizability. We also can support a slightly lower form of strong consistency, which is session or sequential consistency. So all of that is for reads typically. And the writes are always consistent. There's no data loss and so on. Aerospike also supports rack awareness. In the presence of rack awareness, right? I mean, rack awareness has a very good advantage that sometimes when one rack is available, in this particular case, if you have 2 copies and 2 racks, all the data is available in both racks. So reads can happen very well with low latency across both those racks. Again, if you're using sequential consistency, or you can just access a local copy. Writes, on the other hand, essentially have to go through both copies. Now, in certain situations, you can allow the one of the racks to continue. In this particular case, we can configure the majority rack in a 2-copy system when the other rack is disconnected or down to continue with both availability and consistency. And we will use that in this particular case of a distributed setup. Here is a system that is typically, used in certain kinds of applications like interbank money transfers, where it is okay to trade off what I would call as a higher write latency. In this particular case, the system is a 3-copy system with 3 racks distributed across the continental United States. And what you have here is the ability for local apps, because it's a 3-copy system with 3 racks. The local app can read locally because every site here essentially has a full copy. So your apps can always get reads of less than 1 millisecond in steady state. And a write, because of the way I described it earlier, it's going to write to all 3 copies. It's going to be somewhere between 100 to 200 milliseconds, depending on the various networking delays, speed of light considerations, and so on. The end result of all this is it is a completely active system. And if an entire rack goes away, or is either in a split brain mode or it's down for maintenance, what you can have is the other 2 racks can continue to run with both availability and strong consistency. There is no conflicts. There are no conflicts in the system because it's completely avoided given the write all, read one strategy. And when a node goes out with no operator intervention, system continues. When a rack goes out with no operator intervention, system continues. And when a rack comes back on and rejoins it, again with no operator intervention, all of the data, like I described, the whole migrations and how it works, all of this is actually taken care of automatically. So it generates very high uptime. Of course, you do pay for it by having 3 copies and 3 nodes, but the uptime is really worth it in this particular situation. And the trade-off is to have a higher write latency, which is actually acceptable to the applications. There are setups I am not going to describe in this presentation, which are asynchronous, where you do not have to trade off the write latency, but you trade off somewhat in terms of consistency to do asynchronous replication across multiple clusters. And this one is basically a synchronous active-active replication across a single cluster split into racks. Finally, to give you an idea of the kind of performance and the results that are capable in the system that we have described so far, essentially, I have here a petabyte scale benchmark. Essentially, it's a petabyte database which can be compressed to about 1/4. So it's 250 terabytes of data for a single copy, with another copy given as 2 copies here. It's 500 terabytes of data because of replication factor 2. And the uncompressed data size is 1 petabyte for a single copy. And it has about 500 billion unique keys. Essentially, all of this can be run on 20 i3EN nodes. It's probably going to be slightly fewer if you use i4Is these days, but fundamentally, we can run millions of reads per second with a latency of less than 1 millisecond. Now, if you relax the latency, you can probably go up in terms of TPS, but we tend to keep the TPS measurements as long as you can keep that's kind of how we measure this. The latency is less than a millisecond. As you can see, even in the 80-20 read-write case, we can do about 3 million reads per second with 100% of those reads with less than 1 millisecond, and about 750,000 writes per second with 99% under 1 millisecond. All of this is a pretty impressive results, and which I think many of those use cases I described earlier leverage to their advantage. Finally, to find more information, you can go to developer site. You can also find some of the early chapters of book on Aerospike, as well as join our Discord community, and if you can find examples on GitHub and so on. Thank you very much for your time. I'm happy to answer any questions.
Okay, great, Srini. Yeah, I'll coordinate some of the questions coming in. In terms of first one, Srini, you mentioned since Aerospike has 10x fewer nodes, each node tends to do 10x the transactions. How does a node not get overloaded or bottlenecked, or how can Aerospike process even more throughput for any one given node? I guess it's kind of a couple questions there.
Yeah. So the interesting thing here is there are modern processors are multi-core, and there are techniques that we use, CPU pinning, through threads, NUMA pinning in terms of across these processors, as well as our ability to align network requests to individual processors as well as if you use something like a NIC card, like the Intel's ADQ, we can get further streamlining, if you will, of requests coming in to a single node. All of this essentially is a simpler way to describe all of this is to say that we really leverage the parallelism of everything that is possible within a node, be it processor, be it networking queues, be it the number of SSDs in it. So we can actually reduce all the bottlenecks within the system. And many times we talk about Aerospike running at network speed, because once you get into the Aerospike, all of our efforts have been about engineering a system which avoids bottlenecks within the system. And that's how we are able to achieve this level of transactional throughput on a single node.
Interesting. Yeah. So if SSDs are one of the elements, I imagine you could just add more SSDs to any given server or set of server nodes and then increase the throughput, it sounds like.
We can increase it so long as we are able to keep the parallelism going on the processor side and the networking side. So there are obviously always limits, but I don't think we have hit those limits, or even though when we hit those limits, there is new advances in SSDs. You know, from the beginning, Aerospike has been running on SSDs for a long time now. And then we had, PCIe, we had NVMe. I mean, we got a lot of, and we even had something like Intel's persistent memory, which came and went. And there is more on the way with CXL. So we intend to be making use of all of these technologies as they come and go in some way, and we are ahead of the curve, so to speak, and leverage them in order to drive more transactional throughput on larger amounts of data with a lower latency.
Yeah, or if you're not at DRAM nor CPU limits, you could add more SSDs, most likely, yes. It sounds like. Okay.
Absolutely. In fact, we've had systems which have dozens of them, like 50, 60, 100 sometimes. Very rarely. Most people have about anywhere between like a dozen to 20 SSDs, but you can do a lot more, and we've seen that 10 years ago even.
Okay, very good. Next question, maybe basic, but are partitions in Aerospike parlance the same as shards? And what if the records are different sizes? Couldn't there be hotspots still introduced in the Aerospike system?
That's actually a very good question. The interesting thing about, let me take the first question. You can consider them as shards. We say partition because we have partitioned the key space. Our partitioning is, I would say, based on the hashing I described. It goes to exactly 4096. We don't change it. So the whole philosophy of Aerospike is Aerospike, using properly randomized cryptographic hash algorithms, is able to distribute data in the best way possible, that it is not possible for somebody else to do a better job, because it is the math of the algorithm and the way we distribute it, as well as the adjustments like the uniform partition balance algorithm, which make it happen. So fundamentally, we are able to uniformly distribute this data across. So sharding typically involves how it's used is you understand the data characteristics and you try to shard it differently based on different data. We have kind of tried to stay away from that. And the system automatically takes care of it. So the applications don't have to worry about clustering and moving data around and so on.
Okay. Next question, you talked about synchronous, active-active synchronous replication. Does Aerospike not have asynchronous, and what are the high-level pros and cons of each?
Yeah. Today I've been focused on how we deliver a strongly consistent system using Aerospike's high-performance algorithms. The reason I did that was because typically NoSQL is essentially has a reputation of giving up consistency in order to deliver performance. Aerospike actually delivers very high performance and also delivers strong consistency. Additionally, Aerospike also has the ability to relax this using an asynchronous replication strategy, where we have a system, we have a technology called XDR, stands for cross data center replication. Is really about cross-site replication, because data centers, in the presence of cloud regions and so on, don't really make as much sense anymore. They're just one of many different sites. So we can actually have asynchronous replication between Aerospike clusters, and that has a different trade-off. Essentially, you've traded off consistency in order to have better write performance, for example. And the consistency itself varies, and we can set up a system in some cases which is able to deliver what is called eventual consistency or convergence, or we can also deliver something which is strong eventual consistency in a subset of cases, which is also possible. And essentially, Aerospike has the ability to trade off strong consistency systems, which are active-active, versus, I would say, asynchronous active-active systems, which support convergence.
Got it. Okay, I guess we have time for one more question. You talked about on a slide Aerospike's hybrid memory architecture. Are you telling me that Aerospike cannot do in-memory for its system? Why should I care one way or another?
Yeah, can you repeat the question, please?
Yeah, I think the question has to do with the comparisons and contrasts between in-memory and hybrid memory. And is hybrid memory the only way that Aerospike can manage?
That's a great question. The reason I brought up hybrid memory was in the scale-up context. Aerospike also has a fully functional in-memory system where we put all our data and index in DRAM, and we are able to deliver high performance on that. The only thing is, it will not scale up beyond the amount of DRAM that you have in the node. As we go forward, we will support compression and so on in memory systems. So that will also increase the ability of having larger in-memory deployments. But hybrid memory deployments will be able to deliver compression in terms of server sizes. And some of it is important, right? Putting more data in flash as opposed to DRAM means you use less power, less space, and you have a more sustainable data center for handling huge throughputs, so to speak. One of our customers, for example, were able to, after they moved from a different system, which was a purely in-memory system, it was not Aerospike, they moved to our Aerospike's hybrid memory architecture, and out of 6 data centers, they actually literally shut down 2 of them. So there's a huge sustainability argument in order to have real-time systems run on the hybrid memory architecture. And for smaller size scale systems, which require high throughput, you can run an in-memory configuration of Aerospike also. In fact, many telcos do that.
Very good. Well, I don't think we can end on a stronger note than saving customers 2 out of 6 data centers. So with that, just to remind folks, we will be making the slides available. Of course, there will be a replay of the session. Aerospike invites you to visit us at any of these QR codes. Srini, any final comments?
Well, I hope you have learned something about how Aerospike has leveraged some of these technologies to build strongly consistent distributed database systems. I hope this has gotten you curious enough to take a look at us, and we'd be very, very happy to get your feedback. And if you have any questions, you can reach out to us through developer.aerospike.com. Really appreciate the time you've spent today. Thank you.
Thanks, everyone.